pressure there. We looked at this second order system, so that has come up repeatedly. We found the poles, found the segment on the real axis, we found the asymptote, we found the departure angles from the poles, and the arrival angle at 0. We went through the Ruth criterion. This is a good example. Basically, if you set up a quadratic equation like this, with let's say an A, a B, and a C here, you'll find that those coefficients end up just being A, B, C, right? So you have 1, K, and omega n squared. That's basically what you come up with here. So that's just a quick reminder. If you just have a quadratic equation, it's relatively straightforward. Good. Rule 6, we had a double point, which we knew. We basically had two solutions to this discriminant equation. One was here, one was here. Basically, one is on our locus because we're only looking at positive zeta values, which are essentially positive k values. So you basically know it's some, and basically the negative branch, this will show up as a double point, but it's not interesting to us for our real life systems. Good, okay, so I think this is where we ended. We put it all together and we ended up with a root locus. So we had these two branches. We basically have two poles. One goes along the circle here and then off to infinity. The other branch comes around the circle the other way and then heads to that 0, right? So that's in sum the locus of our damping curve. So we have, yeah, as I said, starting point k is equal to 0. That's we're basically treating this as a kind of set of parametric curves depending on the gain for whatever parameter we're interested in, right? So we should be able to extract any parameter where it's linear in our characteristic equation, right? So as we vary the value of zeta, in effect k here, is exactly what we got the last time, right? We had that double point there where basically the branches meet and then go off in opposite directions. There's that angle condition there. And then as we set k to infinity, basically we head off either to the asymptote or to this 0 here, right? So this is another endpoint. Good. All right, so this should give you an idea of what we're trying to do with the root locus. Of course, you can plot it in MATLAB. It can be your rule 0 is just plotted in MATLAB. So if you're doing some serious controller design, that's exactly what you would do. Right, you have these branches here that basically from the equations we know have to be on a circle, really just from the formulas. But of course, if we have higher order systems, we're then just kind of sketching the curve based on whatever knowledge you have of cubics and higher order curves. So that's, again, not really precise, but then at the key points, where basically these rules we're picking up the key points, right? The start and the end and the double points and things like that. And then of course you can take a bunch of like test directions if you want to sketch points on the locus and follow those, magnitude conditions and the angle conditions. That should tell you where a point lies on the curve. But again, MATLAB is really the choice of the designer here, right? So this is the same locus plotted in MATLAB using that R locus function with omega n equal to 2. Basically then gives you the radius of this circle is your natural frequency. Okay, so that should hopefully have been a good example to go through. Simple example, not a lot of poles, well, 2 poles, 1, 0, kind of like the simplest and still interesting example. So what we'll do is now look at the idea of root locus in control, right? So how we would use it to essentially design a control system. Right, so what we're going to do then is look back at our example of a second order system with proportional control. We kind of looked at that in the general sense and said, what does the P control do? What does PI control do? What does PD control? So what I figure is that a good example to look at these controllers essentially in this root locus form, because basically we end up with a bunch of formulas that said, this is what's going to happen to zeta, or the damping of the system, or the effective damping of the system is what's going to happen with the resonant frequency and whatnot. And now we'll basically see that graphically, what's going on with this root locus approach. Right, so we'll take the simple system. We won't worry about disturbances or anything like that. Any kind of anything in the feedback branch there, which basically means we'll treat it as that unit feedback system, just having blocks in this area here. So we all have the transfer function, the closed loop transfer function for this pretty much memorized, I should hope by now. And what we'll do is take, just as an example here, a damping ratio of 1/2, just because it's let's say an interesting point on that curve, right? So we'll basically take the point here, right, on right at the midpoint of that real segment there. It'd be more there. Right. So we'll basically say we have a system. It has this damping ratio. We'll leave the natural frequency in there as a variable, just so you can see what happens in a more general sense. But that's kind of the plan. So we have this transfer function here for our plant, and then our controller is just going to be a proportional control, and just basically absorb whatever constant here, whatever gain we have into that K. Right? Okay, so that's our closed loop transfer function, and as I said, what we're interested in is the denominator. So this is essentially our characteristic equation in that strange sort of rational polynomial form. Of course, we can multiply it out and basically solve the numerator there. Right. So our rules 1 and 2 will condense into one page here. So it's basically we have 2 poles and no zeros. We solve our characteristic, or the denominator there, for our starting points, which are those special points on the unit circle, right, at that 30-degree angle from the upright there. Right, so we have essentially explicit formulas for that. That's just why I chose 1/2 here. Right, so these are our starting points here, and I've just traced out this circle. That's basically our from our other locus, right? It's not critical to this locus that we're doing here. It's just saying if you basically now you could, if you follow this dotted line, this would be changing the damping ratio of the physical system, and we'll look at what happens to the proportional control in this case. So just keeping in mind this circle is here for our damping ratio and not the locus that we'll generate. Good. So we have an even number of poles and zeros, so we don't have any segments on the real axis. Rule 3, we have asymptotes, and they're centered at that point alpha, which we get by plugging in the poles and zeros into this formula. Our n is equal to 2 and m is equal to 0. So kind of not surprising that this point will show up right here between the two poles, right? So that's the center point of our asymptotes, and equivalently that branch point of loop transfer function. Right, and then we use those formulas for the angles. So we have basically angles at just one branch coming out of each of the poles, because we don't have any double poles at any point. So we can plug those right into our formulas. So one is basically pointing vertically up, the other one is pointing vertically down. Good. The angle of departure. So this should be straightforward. We basically have, we're interested in one angle of departure and we only have then one other pole to deal with. So we can plug that right into the formula. We get a minus 270, which is essentially plus 90. And here at the other point, we basically then, that angle condition, as I said, it's valid by using the poles as test points. So again, everything has to add up, and that just means by solving for that other departure angle, we have minus 90, which is then pointing downward in the other direction. Right, so again, this departure angle, we basically formally define a small radius around the pole and then find a limit. But basically, if we found that limit, it would just say that the angle condition is still valid, which is where essentially these formulas came from. Good. Rule 5 for our proportional control. Again, we end up with a quadratic equation. So we basically find the numerator of this thing here. We have that quadratic equation. We fill in our Ruth table. Of course, we can do it formally here. But what we find with the quadratic equation is we basically just have the coefficients of each of the terms here, right? So they just all have to be positive, right, as the three conditions. And then, of course, if you let A be positive, then it would, to begin with, by dividing by, say, minus 1, it should all sort out anyways. So basically, our natural frequency is going to be positive, and we just end up with this omega n squared plus k, that last coefficient. And because we're just looking at the k greater than 0 locus, so our parameter is going from 0 to infinity, we don't worry about negative values. This is always going to be stable, right? So there won't be any points where it crosses over that imaginary axis. Good. Our double points. So we'll just formally go through this. And we see we have that a, so the denominator of the loop transfer function. We take its derivative. We have the numerator and its derivative. And basically we'll go through this. Discriminant here, we find this thing here, the 0 helps a bit. And we solve this, we end up with this value here, which is that point there. And basically what we'd find is that this is not on the locus, right? So it's basically an effect. It might be at k is equal to 0 or something like that, or an imaginary value. But basically what we would do is then check, using the angle condition or magnitude condition, if this point is on the locus, and in this case it's not, right? So we have an example here of, again, a double point, which is mathematically there, but does not help us with our real world system. Okay, that is all of our rules for that example. And basically then what we see is that we have that departure angle going upwards. It's the same as our asymptote, which is centered at this point, minus omega n over 2. So our locus basically goes from those points and then off to infinity, right? Okay, so when we looked at that P control now several weeks ago, what we found is that the P control, by increasing the Kp, would increase our angular frequency, which is exactly what's happening here. So we're going up this axis, which is saying that the angular frequency is increasing, and then our damping is being decreased, which is again basically that angle from the imaginary axis, right? So our zero damping point was here, and as we went around the locus, we got to that critical damping point. So basically between 0 and 1, it's basically the length of, or the ratio of this length here is our damping. Equivalently, the angle now. So if we're increasing the angular frequency, basically we're increasing the diameter of this circle here and pushing the angle closer to this axis here, right? So we're actually decreasing the damping, which is that angle, or the inverse sine of the damping ratio, right? Right. So that's basically things we knew already, right? In terms of just mathematical formulas. That, you know, changing the KP for our feedback is changing the behavior, and this now shows us graphically in that Laplace domain what's going on, right? So why the angular frequency is increasing and why that damping is being decreased as we increase P. Okay, so I see a question elsewhere. The damping ratio, sorry, someone asked the question where we got the damping ratio of 0.5. That's just a value that I chose, right? So basically what would happen now, basically if you did this for a different damping ratio, it would move the pole along this circle here, and we'd end up with essentially the same results, right? It would go vertically up, right? If now our poles are here, then something different is going to happen, but they're going to move together and then go off in the same vertical direction, right? So that was just a value that I chose, basically because we need a specific starting point, right? I don't want to get into varying two parameters just yet, but we'll do that soon, not to worry. So that's just saying, like, if you have a mass spring damper system, a simple second order system, and it has a damping ratio of 0.5, you could then, and a fixed, I basically chose this as the omega n is also just chosen arbitrarily as a kind of normalized factor to be on this circle, right? So if we increase the natural frequency of the system by, changing the spring or whatever, that circle would be bigger or smaller, right? So we end up with, the real and imaginary parts of the poles end up being the damped natural frequency or the resonant frequency. And then the damping ratio, this is well, they're both dependent on damping ratio and natural frequency, right? The two parameter normalization. But again, if you move this around on this axis, the root locus would look essentially the same. Okay, so just to summarize here, just as a kind of additional reminder, the root locus has to be symmetric with respect to the real axis, right? So when we have transfer functions, they're ratios of polynomials, and they're going to have real coefficients, and basically they either come in real roots, so on that real axis. Yeah, okay, so there's a question there. I'll answer it with this graph here, right? Sorry. Yeah, so, right, the transfer function is it's basically ratios of polynomials. We know the polynomials have either real roots or complex conjugate pairs, right? So they could all be real, they could all be complex conjugate pairs, but basically it means like if you have a cubic, you either have 3 real roots or 1 real root and 2 complex conjugate, which basically means the pattern of poles and zeros in the complex plane is symmetric with respect to that real axis, which basically means that the root locus has to be as well. So that's kind of just a reminder when you end up sketching the root loci that they basically have to be symmetric with respect to this axis here. Good. Basically then we could then look at our controller tuning problem as finding key points on the root locus, right? So here, this is the same root locus plotted on a different, like this is basically what we got. This is the same thing here where we said this is natural frequency 2, gives us this circle here. And then increasing the natural frequency of the system increases the radius of the system, which is why we have this strange sort of polar plot here. And then these real lines emanating from the origin are different damping ratios. So that's what's plotted along here. Right, so these radial axes are basically different damping ratios, and basically our zero damping point is that the points on the imaginary axis, which would then essentially oscillate forever, right? Because they have no damping, no friction, nothing like that. They'd go on forever and essentially be unstable. Right, so what we can do with this grid here, this is in MATLAB, it's called sgrid. So if you do your rlocus function call, and after that you type in sgrid, it will put this the damping ratio and natural frequency grid on there, right? So with this simple example here with proportional control, we basically move the poles around with the gain there, the Kp, and what we could then do is, choose a natural frequency or choose a damping ratio that we want and find where that intersects with the locus, right? And that basically then says we can really design the behavior of the system. It's just a question, is there a point on this locus that satisfies our design criteria, right? So it basically now gives us a kind of graphical tool of pole placement. In this case, it's not hugely helpful, right? So we knew that when we applied our P control, it kind of got us close to our final value for that second order system, but not exactly there. So that just shows you the limitations of P control, right? And basically what will happen now is we'll be able to design our controllers. We take, for example, our PI or our PD controller, and that will essentially add, or in general, adding a controller is going to add poles and zeros, and it's going to move these loci around in different ways, right? So that's what we'll do next, is look at the PD control. But really the idea now is I can move these around, and pretty well I can, with one parameter family, I can either choose my natural frequency that I want or choose my damping ratio, which again are parameters which influence the behavior of the system, right? So things like overshoot and rise time we can influence by modifying the poles and zeros. Okay, so that's basically what is up next. So this sgrid again, it's really only valid for a second order system, right? So these complex conjugate poles, but what we'll generally assume when we're designing controllers is that we have, one or two dominant poles, right? So we might have a system here with poles over here and poles over there as well, but these are going to be the main influence on the response, right? In that idea of having dominant poles. Okay, are there any questions about those examples? Okay, thank you. Good to know that someone's still there. No questions. Yeah, hopefully that was those are straightforward examples. So rather than going to a bunch of examples with like a huge number of poles and zeros, that makes a really interesting design. The S grid is really just it's a function in MATLAB that will plot instead of your Cartesian XY axis a polar axis, right? I'll come back to it in these notes. Let me just jump back. Right, so basically what happens is if we take our second order system, we know it's parameterized by that damping ratio and the natural frequency, right? And as we found from that first example, so this was our first example, by varying the damping ratio, right? So basically the radius of this circle here is omega n. So that is the natural frequency depending only on the spring, right? Not on the damping. So that basically gives you a physical parameter that you can vary, which would increase the diameter of this circle. And then the damping ends up being an angle on this, on the unit circle as well, right? As long as we're below below the critical damping, which is usually what you'll want just because just to make the system as fast as possible, right? So if you go into beyond critical damping, you're slowing the system more than it needs to be. So we kind of forget that part in the S grid. But that just means so that this grid here, these radii, the constant radii values trace out circles, and then varying the damping ratio, we have these rays from the origin. So along this axis, you see there's 2, 4, 6, 8, 10. Which means in the example that I chose here, right, there we I put it this one, right? So here in this root locus, I chose omega n equal to 2, just to have a value to plot. So that would be that circle there, which means those poles are on that circle at that 1/2 damping ratio point, which in this case is 1. And the locus goes out from those points, right? So we have constant natural frequency are the radii, and then the rays from the origin, the angles are essentially the damping ratio. So that's essentially now, this is what we can do by varying k. So we can then choose one or the other, right? It's a one parameter family, which means if I say this one parameter family has to be equal to let's say the damping ratio, then I can solve for the parameter value for the k. I can't choose them both, right? I'd need 2 degrees of freedom. I'd need essentially 2 degrees of freedom, which is then what we do by introducing additional controller terms, right? So in MATLAB, it's just calling S-grid, and here it just shows you the damping ratios and then the natural frequencies. And again, it's really the S-grid to repeat. It only applies to a second order system with those 2 poles. And what we're doing when we say this system has a damping ratio, if it has more poles than a second order system, where it's kind of a pseudo damping ratio and pseudo natural frequency based on the fact that we're looking at the dominant poles, right? Those ones with the smallest magnitude of negative coefficient, which is the slower decaying exponential part. Excellent. Good. Yeah, it'll come up again in this set of notes here, because we're really looking at the idea of controller design. So what we'll do now is look at another root locus example. It's our PD-controlled second-order system, which means we basically have two parameters to deal with, right? And so hopefully in this example, we're going to be juggling two parameters, but hopefully it should be clear what's going on. And that's really part of our root locus design, right? So basically if, sorry, I should also, one last bit of this one here. Again, if you remember, if we make K too large, we might not have a physically realizable signal, right? It might be sending a signal to the controller to say, the motor voltage has to be 300 volts or something like that, which doesn't help if we're limited to 10 volts, right? So again, this is like sending K off to infinity is not realistic in every sense, right? There's strange cases where, like in op amps, where the feedback gain is very, very large for good reason, but for when you're running a motor, you don't want infinite gain because you can't then generate a real world signal that will generate that and not fry your motor. Okay, so as I said, we're going to look at, rather than looking at a root locus with 100 roots and poles and zeros, we're going to go to the PD control, and we're going to end up varying two parameters. And we'll see how we can then essentially move the locus around to give us a bit more freedom in our design. Right? So looking at controller design criteria then, of course, these things like rise time, overshoot, settling time, and tracking error, those are all things that we looked at before, right? So our simple step response, in some cases, we don't want too much overshoot. We want a short rise time, so we get from A to B in an efficient amount of time. And then, of course, we don't want the system oscillating, so settling time ends up being important. And then, of course, the other one was that tracking error that we looked at with system type. Right, so, by choosing a controller, we then essentially fix the system type for the most part. And then varying parameters, we can then change the tracking error. Sometimes we can bring it to 0. Sometimes not. It really depends on the structure, but tracking error is, again, another one, right? So we could then use our two parameters, let's say, to reduce our ability to track a ramp input, the steady state error on that, right, to make it smaller. So these are all things we're interested in doing. When we design a controller, we'll look at finding the values, right? So the first thing is finding the K values, like the gain values, which if we have a fixed locus and we're varying one parameter, it's straightforward enough to find the gain just because of the magnitude condition, right? We had that right-hand side magnitude has to be equal to the left-hand side. That's relatively straightforward. But then what we can also do is do things like placing zeros and poles. We add a controller. In the case of our PD controller, what we end up with is an additional 0 that will change the shape of the locus. And we'll just look briefly at placing those poles and zeros. Right? So just adding some degrees of freedom, and the root locus really shows us how we're changing the dynamics of the system in a more visual manner rather than looking at those formulas with all the Greek letters in them. Right, and then the last thing we'll look at is dynamic compensation. It's really a kind of variation of our PD and PI, which gives us a bit more freedom in our controller design, but it should be a pretty natural extension. So that's, in that sense, dynamic just means going beyond proportional control, right? So adding derivative and integral terms. Okay. So, as I said, what we'll do first, the first example here is we'll look at PD control in this, the form we most commonly sought, where we had the Kp, which is multiplied into the two terms, just a proportional term and a derivative term. So TD is then essentially a time constant of our derivative term, right? Which basically says if it's very small, we're looking not very far forward. So if it's 0, essentially we have a proportional control. And if it's larger, we're essentially extending our sort of predictive time. Right? So that's how the TD ended up there. So again, I'll just take the example of zeta is 0.5. So that's basically saying the system, that's the parameter of the plant we want to control, just so we don't have too many parameters to vary here. Right? And we have nice simple equations. So we'll take this controller, this plant, we put together our closed loop transfer function just for reference here. As I said, we're really interested in this characteristic equation in the denominator, and we just put that then into our root locus form, right? So we have the monic polynomials in the numerator and denominator, and that just means that for our k that we're varying, it's actually equal to either kptd with the system gain and the natural frequency squared, or in terms of the ki, which was just kp times td. That's basically just saying we're varying the gain of the system. It just means if you want to find specific values, you have to remember that this k means this or this for our rules. Okay, so this one's a bit more interesting. We have poles and a 0. So the poles we went through before. It's the solution of this quadratic equation. Again, just because I chose zeta is 1/2, it's at this sort of halfway mark along the radius. And we know that as that point root 3/2 in the imaginary direction. Right, so the only sort of addition to this is that we have now added a 0, right? So adding PD control instead of just the P control, we end up with an additional 0, right? So that one is completely dependent on that TD parameter, right? So if we go through the algebra, in this case, the S value is at, the 0 value is at -1/TD, which basically says that if TD is a very small value, this 0 is way off at infinity, right? So that's kind of what we'll end up with is you don't want to look too far ahead. That kind of reduced our stability. So basically now placing this pole is going to be an important part of the controller design, right? So finding the TD and then the gain that gets us where we want to be. Yeah, and hopefully that's all kind of sorted out by the end of this root locus. But basically it says we have 2 starting points at our poles, and we then have 1, 0, where one of these nice poles is going to end, and another one has to end up at an asymptote. Okay, so we then have a bit of our locus on the real axis. So that's our rule 2, right? And it just says, you know, these angles essentially cancel out, and what's important is this one here, and it's only 180 on this side of the axis, right? Positive 180, depending on your point of view, which just means we have an axis segment there, and not on this side. Right? So our asymptote, here we get our asymptote formula. It's a bit more interesting here. So we basically add the poles, subtract the zeros, and divide by n minus m, which is 2 minus 1, so degree 2 in the denominator, degree 1 in the numerator. And what we get out of that is that alpha is this negative omega n plus 1 over PD. This is just a bit of geometry here. It's actually not really important, just because we have one asymptote and we know we only have one branch going to it. So the center is not that important in this case. Just showing you here that from the values, it's basically this length beyond this point here. So minus omega n plus PD is over here. Again, the asymptote is going to end up over here, so this point is not so interesting. Just using the formulas just to show you that it gives you the right answer here, and then 180 degrees. So basically our asymptote is off in infinity in the direction of the negative real axis. Good. So the next one is our departure angles. So this was our 0 here. Basically this, if we take the angle here, that one's always going to be 90, right? Because they're complex conjugate pairs. So the departure angle is then going to depend on this 0 angle. So the psi 1. And basically what we can do this essentially geometrically here, right? So the one thing to note here is I've kind of accidentally, for this example, I drew the 0 here so that it looks like this is a tangent, but you should just remember that it's not a tangent. So if the pole were down here and the 0 were way off, you'd see the line would go right through the circle. So it's not a tangent, just make a note of that. It just kind of looks like it, unfortunately, for the values I've chosen here. But basically, I can construct this angle, right? That's the angle I need to measure off when this is the test point. Right? So I choose pole 1 as my test point, and then, as I said, all the angles have to add up, which is what that formula is down there. And basically what I'd find is that whatever this angle psi 1 is, we're going to have the departure angle is psi 1 minus 270, which is this angle minus this much, which means it's always going to be perpendicular to that line there, right? So as I said, this is not a tangent to the circle. The circle I kept for reference, but it's basically always going to be perpendicular to this line connecting the 0 and the pole, right? And we end up with the same thing over here, which is saying this is the 0 angle. Wherever my pole or my 0 is, right, I can move it around by adjusting PD. And this just says that this departure angle is going to be perpendicular to this ray connecting the 0 and the pole in this case, because that one's always minus 90 degrees. So here we have that angle minus 90 is our departure angle, right? So again, it's really this angle is key here. So if I move the 0 around, this is going to point in a 90 degrees away from it. Good. 4b is the arrival angle. Again, the angular formula here basically says that it's going to be arriving at 180 degrees in this direction. Once again, just everything adding up. These are, one is the negative of the other, so they essentially cancel out. So it ends up being some multiple of 180 degrees. Okay, yeah, so we're really covering everything. These 6 rules pretty well cover everything here. So we'll look at the stability of our PD controller. And again, this is mathematical stability that we're talking about, not necessarily good values for your controller, right? So if we go through, we again have that quadratic equation So our coefficients, so the values in our root array, the first column there, end up being just the coefficients of the characteristic polynomial as itself. So we put it in that standard polynomial form. And what we end up with is one relation that says omega n plus k TD has to be greater than 0, and omega n squared plus k has to be greater than 0, which means our regions look something like this. So this one should be straightforward enough. The k greater than negative omega n squared. That basically says for this coefficient to remain greater than 0, k has to be just less than negative this thing here, right? So this is the line here, which says k has to be on this side. And then this one here, the k times TD relation ends up being a hyperbola with that intercept, right? We have these key points on our standard hyperbola. This is basically an xy is equal to 1 type hyperbola. So that would be negative omega n, right? And then depending on whether omega n is greater than 0 or smaller than 0, this line will be either on this side or this side. You know, when we square the value, does it get larger or does it get smaller, depending on whether it's greater than 1 or less than 1. So this is a rough idea. So this says we have this really strange stability zone where we could actually have negative parameters. And this is just to say that these are the values that are going to keep the locus on that negative real half of the complex plane, right? It doesn't mean you want to set your parameters to any of these things here. It's really that the idea of asymptotic stability is that over essentially an infinite amount of time, your response will decay to 0, right? Which means it could be a very, very slow decay. It could be a really poor transient behavior, which you would get from using, let's say, negative values here. It's just saying that mathematically, this is a stability range, which isn't necessarily a good design criteria, right? So just having a stable system is not usually enough. We want a good response. So that would basically further restrict the parameters, as we'll see coming up. Good. Right, so yeah, this comes from, we have two parameters. We have k times TD, that if you basically remember the equation of a hyperbola is something like this, is a constant. This is our basic hyperbola that defines the logarithm function, as you remember, the 1 over x. Right, it's there, and then the negative version is on the opposite pole, or opposite quadrant is the word. Oh yeah, our rule of 6. This ends up being a pretty big formula here. Right, so we have our denominator polynomial, our numerator polynomial. We differentiate, we construct our discriminant. We'll end up with a quadratic equation in S. Right, so if we essentially write out our quadratic formula for these values, assuming just general values of omega n, which determines this here, the radius of this circle, and then the TD, which places our 0. This is going to be different, but of course we can get a rough idea of what's going on. So that should not be there. The X is jumped in there somehow. Right, so we start at this minus TD, and we have plus or minus points. Basically, the one over here is going to be on the root locus, and the one on the other side is not. We don't need to go into too much detail with that. just because we can plot the locus in MATLAB. That's what I said is, 4, 5, and 6, rules 4, 5, and 6 are essentially, good to know, but some of them can be rather tedious. And this basically says that if we have reasonable values, this is always going to be positive, whatever's under here, right? As long as we don't choose like an imaginary TD or something strange like that, it's always going to be over on this side, right? That minus -1 over TD minus whatever the square root of this is. Basically, that's always going to be positive, which means it's always going to be somewhere over here. This is just to say also this is not to scale, right? So I haven't marked off this distance either, right? But it tells us that there's a double point. Good. Okay, so what we'll now do is look at some of the results of this root locus that we got from MATLAB. So again, we choose omega n equal to 2, just so we have a real fixed system. And then what I'm going to do is essentially change the value of TD, which then places the pole, or the 0, sorry, right, of the controller. Right? So if we think back to our example of just the P control, we had those 2 poles there, right? On this scale, we see that's our circle, on our circle of radius 2, right? And what we had with the P control is that the locus essentially went parallel to the imaginary axis there, right? So it basically went off into infinity in the vertical direction. It was positive and negative. And what we've done now is we add a TD, a derivative control with a very small TD, or relatively small, 1 over 16, which basically places the 0 at minus 16, which you see here on the scale. So you can see this circle now has a relatively large radius. And what the 0 has essentially done is pulled the root locus down away from the imaginary axis and wrapped it around, so that we have one locus going around to that double point, and then back to our 0, and then the other one going around to the double point and then off to infinity, right? So if we set TD to even smaller values, right, so that our differentiating time starting at 0, our locus would be way over here, and then as soon as we add a tiny epsilon of a TD, our 0 is going to be way over, let's say near minus infinity, and that circle is essentially going to be very, very large, but we'll basically meet again at that double point. Right, so in essence, if we think of TD equal to 0, we can also think of it as a circle of infinite radius, if you are interested in strange limits of geometry here, right? So basically moving that TD in is going to pull our root locus closer into the 0, right? So here, if we then make TD a bit longer, so a quarter of a second, that pulls the 0 into 4, right? So we have the same rough shape on a different scale. Again, that's our circle of radius 2. And so as we're pulling the TD in, again, the locus gets pulled closer in. So we can then keep going, make TD longer. So for 1 second, we basically have everything lined up there. And that looks strangely like our damping ratio curve. It's shifted a bit. And then, of course, we can make TD longer, which is, looking further to the future. And again, basically what's going on now is that we're modifying our damping ratio. or basically, yeah, sorry, moving around the locus so that we can essentially adjust our natural or resonant frequency and damping ratio. Good. So yeah, that's the last example. If we set TD very large, our zero gets closer to the origin, which basically shows you as we move that zero in, it's pulling the locus along with it, right? So for a small TD, we essentially have P control, right? So that zero is way off at infinity, and those branches will be going essentially straight up. And then as we set TD longer and longer, that zero gets closer and closer to the origin, right? And really that's what I said, is that addressing that zero is going to pull the locus with it along that negative real axis. Great. So the moral of this story is now we have 2 degrees of freedom for our controller. So we should be able to now, with certain limitations, right? As I said, if we just had P control, we'd have our root locus going straight up along there. And as we add a little bit of TD, the locus basically wraps around here. It might help to have like a video of that, moving the pole in and seeing how the locus changes, but I think you get the idea. But that really gives us a very big range of what we can do with these poles, right? So now if we took just this example, TD equal to 16, our locus basically starts here and comes along here to that critically damped point, and then into the origin, and then the other way, right? But basically now if we think of, if we had our S grid on here, we'd say this angle of the point would define the damping ratio, and its distance from the origin would be essentially that natural frequency of the system, right? So here we can't change the resonant, the natural frequency, because we're fixed on that radius there. But again, by moving the zero around, we can move essentially that natural frequency to different points, and using different damping ratios essentially gives us 2 degrees of freedom to adjust 2 parameters, right? So that's essentially what we'll look at now. Good. Are there any questions about that root locus? Okay, yeah, so I think that should be lots of root loci to think about, and just saying that now if we have a controller with 2 parameters, we have more flexibility in what we can do, which means depending on the range of the parameters that make sense, we can essentially set 2 design criteria, right? So here, just as a kind of refresher, we looked at that response when we looked at transfer functions. Just to remind you, we were looking at this type of thing, the step response, where we had something like this, right? So we had that maximum peak, of course, is our overshoot as compared to our set value. We had the rise time, which was getting between 10 and 90%, so we didn't have to do any strange differentiating. Right, so things like rise time depend, let's say, mostly on the natural frequency of the resonant frequency of the system, right? So our natural frequency is this radius here, and then the resonant frequency is essentially where we end up with on that real axis. Right, so our general sort of rule there that we basically derive from a simple second order system, right? So the system we looked at, where we had a spring, a mass, and a damper, and we pushed on the spring side, and it moved the system around. That's kind of, we would take that as a base system with two poles, right? And then again, because we're only looking at two poles, it's in essence a second order system. But if we're looking at designing a general system, we'd say we'd have two dominant poles that are going to determine our transient behavior, right? So we'd say this is, let's say, approximate damping and approximate natural frequency, or pseudo damping and pseudo natural frequency. So they're really kind of rough design criteria if you don't have a second order system. Right, so our rise time, our special formula there was essentially 1 over 3 times the natural or resonant frequency, which is related to the omega n through division by 2 pi. Right, we saw that. And that basically says that this sort of circle here basically determines our rise time, right? So if we push that out further, it's going to affect our rise time, which basically then says, placing the pole will affect the rise time. And then our overshoot was largely dependent on the damping ratio. So this is basically a formula again for that second order system, essentially the percent, the magnitude of this as compared to the step. So basically for different overshoots, we'd have different damping ratios, which would be acceptable. It just means that, setting this angle here of the poles affects the damping of the system, and then therefore, affects the overshoot. Right, so if we have basically, limits on the rise time and limits on the overshoot, this basically sets off a kind of binary, is it too large, greater than, less than, regions, really like we had for stability. Right, and then the other one was settling time. So in this diagram, settling time was basically when we got to some percentage of the final value, which might have been, within 10% or within 1% or whatever. It basically ends up depending on that real part of the poles, because that sigma determines the rate of decay of the exponential term, right? So that sigma, the real part, basically was the coefficient of our exponent, and if it's like a dominant pole or not, right? So it tells you how fast that term decays, and that basically then tells you how long it takes to get close to its final value, right? So placing that pole on the axis is another design criteria. So you can use, maybe you're given 2 of them, right? You want to have a fast rise time and a quick settling time, and you don't worry about overshoot or something like that. But you basically then combine these into a composite region, right? So this is including all of them, basically your rise time, your overshoot, your settling time, all into one sort of composite region, which is then not quite as simple as just saying the right or the left hand side of the plane there, the negative real half. And that's really like what I was talking about before when we said, the Ruth criteria basically gives us a stability criteria, which basically says we're in this half of the plane, which makes mathematical sense, of course. But once we look to real systems, we want to be a little bit more restrictive in their behavior. We do want to limit overshoot, so parts don't bump into each other. We have a bit more of an efficient system in terms of, say, fuel usage or whatever. So it's just to say that stability is one criteria, which basically says it's this whole half plane here. But if we want to then, control our response, design our controller to get the system to really do what we want, we're going to have some other region in this complex plane, which is going to be the acceptable region for the dominant pole, right? So we want some reasonable amount of damping for the system to control that overshoot and things like that, and then the response time. So what we end up having in our, when we're looking at more specific design is a composite region in that, right? And that'll be really system dependent, what you need to design, what you need to do. Maybe just having a stable system is enough, right? Okay, so hopefully you see that we're going to then put this together. We have our root locus method, which is going to tell us where we can put the poles and zeros, and then some criteria is going to tell us where they should be, and hopefully we then can combine those ideas to design a controller. Okay, so we've got a few minutes left here. Good. So we haven't looked at the magnitude condition, right? So you might have a root locus that looks like this here, and you say, I have a damping ratio I want to obtain, which is given by this angle in terms of zeta. And so your simplest design criteria would say, where does this locus, depending on K, hit this damping ratio that I want? So here I've just used the example of the PD controller and some value of zeta. And what we can then do to find the K that we want is use the magnitude condition. And this just says, I can draw out the angle here, and then, of course, in MATLAB you can, click on the locus, and it'll give you the K value. But just to show you where the formula would come from, we basically want this point here, and if this point is on the locus, basically that magnitude condition has to be satisfied. So what we would do is rearrange the root locus equation just to solve for K. That's what we're interested in. So it's -1 over the loop transfer function. In terms of our polynomials, it looks like that. And basically then, if we did the magnitude of both sides, of course, we're looking for a K positive for a positive root locus, which means, that's always going to be positive. And then we take the magnitudes of the complex numbers, the numerator and denominator, and that should basically come out to be K. So in this example, we have where our test point here is where we want to find the K for. We have a magnitude between this point and the 0, and then we have the two poles here, the magnitude and the magnitude. We basically then say K has to be equal to A1 times A2 over B1. So again, looking at that magnitude and phase relation. Right, so in terms of actual, complex numbers, it's basically saying this here, right? So we have our point that we're interested in finding the K for. We subtract the pole 1, pole 2. So these are complex numbers. Complex numbers, we take the absolute value, which is just the magnitude, and then divide by the magnitude of S0 minus Z0. Right, so rather simple formula there. It just means you have to be able to measure off these magnitudes, right? So you either know the poles and zeros and the point, the coordinates of the point, or you use MATLAB to click, and MATLAB will essentially give you that formula, which will tell you the value of K, right? So that said, the K for this should work out to be 0, and that one should be infinite somehow, right? You have to divide by 0 in there. Good. Right, So maybe then the last thing we'll look at today is how we would go about placing that pole right. So as we saw with our PD control, so this is revisiting this example we've just looked at, we can move around the zero, right? So adjusting TD is essentially going to change the position of the zero and basically then move that locus around, right? So when it was off at infinity, our locus basically went vertically in this direction, and then it kind of wrapped around as we moved the pole in. Just that rough description there. So what we might want to do is say, I want this to be the pole location of my designed system, right? So I have my physical system has these poles here. I'm adding this controller so I can basically move those poles around. And let's say I choose as my design criteria, this should be my pole, based on damping ratio and natural frequency. Again, having those 2 degrees of freedom. And so what we can do for this example is, because we know the pole or the zero is going to lie on that real axis, we can basically then use the angle condition, which basically says, if I want this point to be on my locus, that's going to be my test point, my S0. It's going to have an angle to the original poles. So pole 1, pole 2, these angles are then fixed. And basically what I would then do is have a variable third angle, and I would need to find the psi1 that basically placed this point, moved my locus to where this point lies on the locus, right? So forcing the locus to meet that design point, rather than finding the k which passes through a point on the locus, right? So a slightly different problem, basically going from the other direction, and then that would say, the sine of psi1 I get from the basic trigonometry here, saying my 0 is going to be at beta plus j0. The pole I want to have is sigma naught plus j omega naught, right? So I have the sine of that angle, which means that I can find the angle itself and plug that into the angle condition and do some algebra there and essentially solve for where that 0 should be, right? So that would be, I can place my pole by essentially moving the 0 in the controller to the right point. Good. And then the gain for that would come from the magnitude condition, right? So then you'd have your 2 parameters and you'd be able to essentially determine the poles of the new system. Okay, sorry, we're over time. Sorry about that. Thanks for listening, everyone. If you have any questions, I'll stick around here. Have a nice day.